Chapter 16, acids and bases. We're not going to do all of this chapter. We're going to do highlights of this chapter. This is not officially the last chapter. This is the last chapter in your book, but we're going to do a little from chapter 17 also. So there are different ways of defining what is an acid and what is a base. I'm not going to quiz you on these names, but Arrhenius was a Swedish scientist, and his definition of acid was that it was a substance that produces hydrogen ions in solution. So anything where you put it in a solution, and generally these are aqueous solutions, you put it in water and hydrogen ions form one way or another. And bases produce hydroxide ions. Now we have talked about acids and bases before when we talked about reaction types and nomenclature, and we know that an acid formula starts with H. Well, that's the hydrogen ion. When you put an acid in water, it ionizes and produces hydrogen ions. And we learn to recognize bases for our neutralization reactions as being things like sodium hydroxide or calcium hydroxide, a metal with a hydroxide ion. Another definition, Brønsted-Lowry, these are two different people. An acid is a proton donor and a base is a proton acceptor. Like, well, how are those related and how can that mean this, how does that work out? Hydrogen ions and protons. Well, let's think about a hydrogen atom. I was using yellow, the other class. Dark red, I like dark red. So a hydrogen atom has how many protons? One proton. How many electrons? One. So if we make this into a hydrogen ion, H+, we lose an electron, what's left? A proton. A hydrogen ion is just a proton. Okay? So the Brønsted-Lowry is saying that an acid is a hydrogen ion donor. It will give hydrogen ions to something else. And that a base is a hydrogen ion or a proton acceptor. So the definition of the acid, the difference is very, very subtle. The difference for the bases is a little more significant. But if we look at this reaction here, where we put hydrochloric acid, we learned the name of that, and we would recognize that as an acid because it starts with H, HCl. If we dissolve this in water, what happens is that this hydrogen ion will be donated by this acid, and it will be donated to the water molecule. And so we will end up with a chloride ion and this funny looking thing. Because if you think about a proton, would a proton be comfortable just out by itself? Protons I think of as being like a 3-month-old baby. Do you see 3-month-old babies just strolling along the sidewalk, playing at the playground by themselves? No. You don't even put them down on the ground, right? You hold them. So the hydrogen ion, the proton, is a little bit like a very young baby, and it's always with something else. So here it was with the chloride, but chloride needed to do something, and so chloride passed the baby to the water molecule, and now the water molecule is holding the baby. Well, it's a water molecule with a hydrogen ion, so it's now an ion, and it's got a name. I think we'll talk about that later.
Is it acidic water?
Pardon me?
Is it heavy water?
No, it's not heavy water. Heavy water, that's a good question. Heavy water, those are isotopes of water. I'm sorry. They're water molecules with different isotopes of hydrogen. So most hydrogen is 1 proton, 1 electron, no neutrons. There's also deuterium and tritium, and deuterium has 1 neutron and 1 proton, and tritium has 2 neutrons and a proton in its nucleus. And because that significantly increases the mass of the hydrogen atom, it doubles or triples it. That's called heavy water.
Does that affect you if you drink that instead of pretty way?
I don't know that it would. I'm not sure. I should probably look that up because people are always asking me that. Good luck finding any, because they use it, for nuclear weapons and stuff. So
Well, it wouldn't hurt to
well, it wouldn't necessarily, but but you're not going to be able to go to Kroger's or Save Mart or something and just buy it, right? You know.
You're not gonna like drink it by accident.
You're not going to drink it by accident. No.
Okay. Should be testing it before I drink it.
So, yeah, I hate the pink here, but whatever. I like pink, but not with red. Pink and red don't go together. So here's an acid, and this is just some generic acid. There is no element with the symbol A, so this is just some, like a variable. So here's an acid. This donates a proton to the water molecule. The water accepts it. And then we have this, which is called a hydronium. I thought we would have gotten to the name of that by now, but apparently not, so let's give that a name. This is the hydronium ion. Yeah, it's kind of a cool name. H3O+, that's called hydronium. And a lot of times when we write chemical equations, we ignore the hydronium and we actually just write H+ because it's just easier. But that's, it's like, okay, we're talking about the baby, but we understand that somebody's holding the baby, and it's going to be water that's holding the baby. So the hydrogen is transferred from the acid to the base, and then we get this H3O+ hydronium ion, and we have this A-. Well, this is an equilibrium. It can go back and forth. And so if we go the other way, then this one has the hydrogen ion and is going to give it to this. So then this one's acting like an acid and that one's acting like a base. The base is like the babysitter who takes the baby. Base, babysitter, baby. Okay? So, because what does the acid do? The acid hands the baby off. Here, could you watch this little guy for me? The babysitter says, oh yeah, I'll take him, thanks. And so, but then later, the babysitter is going to give him back. And in that sense, the babysitter now is acting as an acid by giving it back. So the hydrogen ion can go back and forth and back and forth. So this is an acid, and we say that this is its conjugate base because these two are related. The difference between these two is that this is missing the hydrogen ion. And this is a base, and this is the conjugate acid. The difference between them is just a hydrogen ion. So the conjugate base is everything that remains of the acid molecule after that proton is taken off, the hydrogen ion. And the conjugate acid is what is formed when the proton is transferred to the base. So here we have Lewis structures, which help us to understand a little bit more. So here is hydrochloric acid. That's a polar molecule because chlorine is more electronegative and the hydrogen is less electronegative. So chlorine is hogging the electrons in this bond. So hydrogen is feeling a little kind of left out to start with. And then here's the water molecule, and there's these two lone pairs here. Pair of electrons not being shared with anybody. And the hydrogen's like, I'm going to go over there because I could get more electrons. I could get more share of the electrons by going over there than I can where I am here. And so the hydrogen will leave this situation. It doesn't take its electron with it. It leaves it there. And the hydrogen nucleus, which is just a proton, hops over here. And now it is sharing those electrons with the oxygen, even though the oxygen had both of them to start with. It's like, you go out for dinner and your husband, well, actually, I have a friend whose husband never orders anything when they go out for dinner. She'll order dinner, the kids will order dinner, and he doesn't order anything, but then he shares with them, right? So he'll share her meal with him. Get your own. But she doesn't because she loves him. But anyway, so I have this meal, and then, my husband, who does not do this to me, but then he's like, we're going to share the food, but it was my food to start with. That's what's going on here. So the oxygen had the dinner, has these two electrons, and is going to share them with the hydrogen, even though the hydrogen didn't have any. So it's not like we're sharing equally where we're both bringing something, but the one is sharing with the other. Okay? So this is the acid, It gives the hydrogen ion to the water molecule, which is acting as a base. Here we have the name, hydronium ion. And so we get this ion formed, which is a hydronium ion. It has a positive charge because this hydrogen was a hydrogen ion. It had a positive charge. It didn't bring the electron with it. And then what's left over here is the chloride ion. So we should learn to identify conjugate acid-base pairs. And the way you do this is you look at the two things that are proposed as a pair, and you say, is the only difference that one has a hydrogen ion and the other does not? So let's look at this first one, HCl and HNO3. What's different about those?
Nitrogen.
Well, one has nitrogen and oxygen, and one has chlorine. That's a lot more different than just one has a hydrogen and one doesn't. That's not a conjugate acid-base pair. So this one is not. How about H3O plus and OH minus? Now those are more similar than the first ones, aren't they? But let's look at this. Well, H3O plus, and this is OH minus. If I took an H plus off of this one, what would I get? I'd get H2O, right? Which is not OH minus. These are more closely related, but they differ by 2 hydrogen ions. And so this is not a base pair either, acid-base pair. How about H2SO4 and SO4 2 minus? Same thing. 2 hydrogens on one, none on the other. So that's not an acid-base pair. HCN and CN minus. If we took this CN minus and added a hydrogen ion, we would get that. You see that? Or you can think of taking this and subtracting the hydrogen like we did up here, and you're going to get the CN minus. Oh yes, plus, thank you. I kind of think I did that and it just didn't show up. But thank you, because little mistakes like that are really confusing. Any questions? Conjugate acid-base pairs.
Which means they can swap.
They go together. One's an acid, one's a base, but they're very much related to each other. So this question is asking us to write the conjugate base for each of these acids. So what does the acid do? It gives a hydrogen ion, a proton, away. So the conjugate base is what's left after that happens. So the way we approach this is by subtracting a hydrogen ion from these guys. So if I subtract an H plus, I'm going to end up with only one H now instead of 2. And the sulfur will still be there. And how does the charge change? I've taken away a plus 1. That means the charge becomes more negative. It was 0, and now it's minus 1. So HS minus is the conjugate base of H2S. How about HS minus? That also has a conjugate base. I'm going to subtract a hydrogen ion from it. So now that one hydrogen is gone, so I've just got S, and the charge is going to go down more negative by 1, so it'll be 2 minus. So HS minus and S2 minus are a conjugate acid-base pair. How about NH3? You may say, well, that's not an acid. Well, but it can act as an acid. Let's just do the same thing, just apply the pattern to it. If we subtract a hydrogen ion from that. So we're subtracting a hydrogen, we end up with NH2, and then we're subtracting 1 from the charge. So it becomes minus. It does actually exist. I don't know the name of it off the top of my head. It happens more when that nitrogen is attached to an organic compound. How about sulfuric acid? We're going to subtract a hydrogen with a charge. So the number of hydrogens goes down by 1, so instead of 2, we have 1. And the charge, we subtract 1 from the charge, and so we have a -1 charge. Does that make sense? That's not too hard, is it? It's just remembering to do it. That's the hard part. So here's the flip side. Write the conjugate acid for each of the following bases. What does a base do? It babysits the baby. It accepts the hydrogen ion. So here we're going to add hydrogen ions instead of taking them away. So phosphate ion, if we add H+, now always put the hydrogen on the front. HPO4. The charge was 3-. We're going to add 1. Now it's 2-. That's hydrogen phosphate ion. So iodate ion, again, to make the conjugate base, we're going to have it accept a hydrogen. I'm sorry, that is the base. It's accepting a hydrogen ion to make the conjugate acid. So we'll put the H in front, and we get HiO3, which is iodic acid. Nitrate plus H+. What do we get? HNO3. Nitric acid. NH2 minus. And H+. So if we're just following the pattern we were doing, we end up with that. We go, that looks kind of weird. What might be a better way to write that? NH3. I would not try to trick you on that. If you gave me that. The H goes at the end just because that's ammonia. But yeah.
It's probably when you're dumb one.
I like dumb questions.
Because I'm dumb, I'd probably write it H3N, but I would mark off.
If you wrote H3N, no, I wouldn't mark you off.
Oh, okay, because that's what I thought it was when you put NH3.
No, that's fine.
Okay.
On the multiple choice exam, though, the choice would be NH3, and then there might be other choices might be NH2 minus or various other crazy things. Okay, but like maybe there'd be NH3 minus or something, but there would not be a wrong answer that was wrong just because of the ordering of the atoms. That's a little detail we don't worry about.
Is it the conjugate base that you said that later can give